All right, good morning. So it's a pleasure to be in IT Bombay. I'd like to thank the organizing committee for all their hard work, the scientific committee, to think that this is sort of a big deal. You see the pressure. I'll be the first speaker ever in MIP International. I'll be the first speaker in MIP International with errors in my theorems. A lot of firsts, okay? But anyways, thank you very much. It's just such a great pleasure to be here. So today I'm going to talk about some duality theorems. This is joint work with my colleague Diego Cifuentes at Georgia Tech and Jingye Shu, who's a PhD student. All right, so let's get started. Right. So I'm going to talk about duality, and the organizers were nice to give me apparently 7 hours. Was it six and a half, and 20 minutes more now. So I can until I fall. Okay. All right. But yeah, I want to talk about duality, and we all know duality. I think a lot of us love duality, and usually we think of a duality in terms of convex optimization, and okay, I'm not an expert in convex optimization, but in some ways, a lot of notions in duality, even if they appear different, like conic optimization, the duals you take, or the Lagrange or relaxations, and they KKT, they all somehow are related, and they're all actually same in some ways. All right, there's some sort of a nice universality to them. And that's nice. But it turns out that actually integer programming is also full of a very rich duality theory, right? So I want to talk about it. It's just that in integer programming, the duality is a bit more different in the sense that they are a bit more difficult sometimes. And a lot of the proofs here are very interesting and nice, but they tend to, for example, a lot of them follow from sort of maybe separating hyperplane theory. There is some sort of a universality to this, but building strong duals for IPs is a little bit more challenging. And what I would argue is that, and that's sort of what I wanted to present at a high level. I'm going to present two particular results together with Diego and Jingye. But at a high level, I thought I'll also have a few introductory slides about sort of building strong duals in integer programming. And I would argue that somehow these strong duals are built with different techniques, and they serve different purposes. Okay, so that is sort of the theme that I'm going to go with. All right, so let me start with the classic dual in integer programming, my favorite dual. This dual sort of has a long history. It's called the subadditive dual. I'm not going to spend a lot of time on that. But one way to think about the subadditive dual was that this was almost an organic way to understand cutting plane theory. So I would say one way to think about the subadditive dual is a way to understand cutting plane theory. And this is one representative theorem. It's for pure IPs. You can do for mixed integer linear. It just gets technical. I can't put it in one slide. If you have an IP, all rational data ax less than equals to b x non-negative integer, then you can show that any linear inequality that is valid for that set is dominated by an inequality that looks like this, where f is a subadditive function operating on the columns of your problem, and non-decreasing and something 0. And any inequality is dominated by something like a subadditive inequality, right? And I don't know chicken and egg, whether the subadditive theory started first or the cutting plane theory, but there's a very nice connection between that. And I'm not writing the dual, but the fact that any inequality, valid inequality for that set can be described or dominated by something like this tells you that you can get the convex hull of any IP using something like this, which means you get a dual. Right, and the recent years there's been some nice work extending this to sort of I would say convex IPs. So with Diego, in his thesis we looked at some of these things, and actually I was putting together this slide and I realized this is a great workshop to talk about it, because pretty much everyone who's worked on this is actually, I think, was supposed to be here any case. Okay, so there is Burak, Akshay, is Akshay here? Akshay will be here I think later. And Gustavo I see here, and these guys have all worked on sort of generalizing this sort of to convex and even more abstract setting monoids and so forth. And so there's a very nice tradition of subarray duals. So let me mention one another dual, which is, subarray dual is sort of my love. But this is a very beautiful set of results. So first proven by Natasha and her collaborator, and then reproven by Jawad, Shabir, and their student with a very elegant proof. And this is a different type of dual. Okay, so what is this dual saying? If you have an IP which looks like this curly X here is a mixed integer set. So X is some components are integer. There are linear constraints. Using rational data, rationalities are important. And then you have this constraint AX equals to. Okay? And it turns out, if you write this augmented Lagrangian, usually Lagrangian is without this, and we'll actually talk a lot about Lagrangians later today. So, but you add this penalty term, which is not just the linear term, but a norm term, then in fact, the value of these two problems is equal. Okay? So there exists finite values of these dual multipliers. Okay? And in fact, you can say more about it in some papers we looked at it. You can actually say that these are polynomial in the size of the input of the data. You get this. So I've written here purpose design of ADMM. At least, in my conversation with Shabir, who was a dear friend, he was designed thinking for the case where this curly set X is decomposable. So think of X maybe having 3 different sets of variables, each of them having their own constraints. And they're all being connected by these linear equations. Okay? And so when you write this dual, now at least your feasible region is completely decomposed. The problem, of course, here is still, in some sense, the objective is, if it was just up to linear, it is separable across variables. But you have this term, right? And you kind of have to have this term. It's very difficult to just kind of make it completely separable. And so I would say, in some ways, the results are very beautiful, and actually there's been some very nice follow-up work, again here. So with Shabir, again, we looked at, instead of linear, we looked at rational convex functions, quadratic functions, and Avinash, Vishnu, and Abhishek here have some. Yes, sir. Great question. So in the pure case, pure integer case, you can, but in mixed integer, you really have to have a norm. And there's some subtleties there. So pure IP, you can actually show that you don't even need a norm. You need like some sort of semi-norm, something. So, like it has to be non-zero if it's outside 0, but its conditions are much more relaxed if it's pure integer. When it's mixed integer, it becomes really, you really need a norm. So you can, and I've written a norm here, but all norms are sort of equivalent to each other. And so you could put your favorite norm here. So you can put 1 norm, 2 norm, 7 norm, whatever. So it's that up to that flexibility for mixed integer. A great question. Yes, sir.
Is the role related somehow to the number of the matrix A, the position number?
Yeah. So in this paper, for example, what we proved is that actually you can select to achieve this soup with some values of lambda and rho, which are polynomial in the size of the input. But it's, to be honest, the proof is, I could tell you the intuition right now. It's almost like it's almost like saying integer programming is an NP. Every extreme point of the integer hull would, but that began, it's not practical, if that's what you're asking. I don't know if I answered your question, but yes, sir. Yes.
And you have like continuous y variables, but constraints are only in terms of the pure variables. You have kind of,
I still think you might need, because I think or maybe no?
You will not need.
Okay, then you'll not need. Okay. The thing is, basically, it's about the value function.
Yes.
And how they're discontinuous in value function. And one way to view this norm is you're sort of sticking it in and reaching every point. So something like this. Okay, so there might be some details there. All right? If you have questions, there are experts in the audience. So that's great. But anyways, I will say that, yeah, again, I wanted to mention this because, of course, Avinash and Vishnu and Abhishek are here. And Martin Schmidt and his co-authors recently actually also used this for bi-level optimization. And so, yeah, so people have, so different purposes, different duals with different sort of proof techniques, different ideas. I will refer back to augmented Lagrangians. In some ways, I would say that I'm a little bit sad that this really did not take off as much as I thought in terms of designing actual algorithms that converge, right? So you have the duality, but then to take it from here, even if this was a block diagonal setting, and to actually prove there's a convergent algorithm that gets you to the optimal solution, we kind of don't have that. Even in the convex setting, this augmented business is very tricky. Like you go from 2 pieces to 3 blocks, the proofs really go crazy. And so, but the proofs are very elegant, especially Natasha's original paper, as it should be, they should pioneer. The proofs are much more technical, but if you look at that second paper, highly recommended. The proofs are very elegant, very nice. All right, so I'm going to talk about 2 different duals today in the same spirit. All right, the purpose is going to be a bit different, and so the construction will be different, and you'll see. And again, have we realized the purpose? Maybe not computationally, but that's where we want to head to. So the first one is called a copositive dual. The first 2 duals that I present is actually for general integers, right? Everything that I'm going to present today is only working for binary, but it will allow me nonlinear, and you'll see. Yes.
So when you ask for convergent algorithms, you're not asking polynomially convergent.
No, finite.
Finite convergent.
Yeah, we don't. The problem with you get stuck in local minima. It's very easy.
Is it known for NP hard problems, like some combinatorial?
I don't even know. If you gave me, let's say, some very combinatorial problem like matching, right? Maybe the graphs are very separable, and then I dualize something. I don't know of a finite convergent algorithm with augmented Lagrangians.
No, we would not solve it without augmented.
Yeah, but it would be nice. That was why people designed it. Yeah, because people wanted to move it to the objective, because then the feasible region is separable. So now you can just fix one of the variables and then solve for the other. And can you do? Yeah, that was the hope, but that never. Yeah, so we have time till tomorrow morning. Someone can solve it. First open problem. Yeah, okay. But is the question clear?
We have some instances in which we can do something.
Oh, great, fantastic. All right, so let's talk about this dual, which is not for general integer. It's only going to be binary, but it's sort of MINLB, sort of. Okay. And the purpose here was different. The purpose here was doing sensitivity analysis for a sort of more classical, when we teach linear programming, we teach duality, and after that we say the first example application is doing sensitivity analysis. And that's what I wanted to look at, and I'll tell you a little bit about our motivation. So basically, we are thinking of problems that look like this, right? There's a quadratic objective. Q does not have to be convex. Your variables are mixed binary, so without loss of generality, I'm going to write it as equations here for sort of the technical things to go through. But really what I'm thinking about is that I have a sequence of problems where the objective and the left-hand side matrix A is fixed. The variables are fixed, the definitions are fixed. Okay, and what is changing is right-hand sides. And personally, I came across these class of problems when I've been looking at some power system applications. Okay, so for example, you do these commitment decisions. So you decide every day or every few hours, how do you want to assign generators? Okay, but the optimization problem that you solve is on an electric grid, which is not changing. Okay, what is changing really is every time you solve the problem is the demand. To be fair, you also change the objective. So really, if I wanted to look at the more general version, Q and C would also change. But for now, let's keep that fixed as well. Okay, so and this comes up in other applications. Anytime you are solving some operational type of MIP. MIP is a great tool. The solver is fantastic, and there are experts here who've built parts of these tools. But to this day, in some sense, it's really very useful when you have a planning problem. When you have an operational problem, MIPS, we still struggle. And what I want to, at least one of the philosophical things that I want to convey with this part of the talk is that we really need to rethink about how we solve these operational MIPS. Because you really should not be solving, right now, from what I understand, like some of these ISOs, they literally resolve the problem every time from scratch, right? They buy their favorite license of their favorite solver, and they just, every day or every hour they have to solve it, they just restart from scratch. And you shouldn't really be doing that, okay? Because the problems are really the same. This A matrix remains fixed because this is something related to the graph, for example, in the power network, the grids, the power lines, the properties of these power lines, the properties of the generators, these don't change, okay?
Do you have any positive definiteness assumptions on Q, or is it
Q is arbitrary, okay? And what I will say is there's some actually very nice work, sort of machine learning applications, not my strong suit, where people have shown, at least in practice, they can find really quickly very good solutions if you perturb the right-hand side. Okay, Dimitri has a very nice paper with one of his postdocs, who's now, I think, in Princeton. Yeah. Yes, Bartholomew, and there are others. With one of my students, especially for power network, we did this. We came up with some very simple heuristics. Your demands is changing a little bit. You take your previous solution, you perturb it in some clever way, and you can construct primal solutions. So the motivation here was dual bounds. Okay, I don't want to just find good solutions. I want to certify it. All right. So is there any questions about the purpose of this dual? All right. So let's move on. So let's look at the construction. And let's go back to convex optimization. So a typical conic problem is a linear function subject to linear constraints, and the variables live in some nice cone. And if you take the dual, it looks basically the same, some linear function, some linear constraints, and now you live in the dual. Okay? What is nice about this dual is that it has two really nice properties. The first one is that you always have weak duality. So by construction, if you take a feasible solution here, you take a feasible solution here, the value of this guy will always be greater than this guy. Just like we teach in LP. I don't know if you've done this fun exercise where you divide the class into two rooms, and one side only computes primal values, the other side duals, and they compare, which is fun. I love doing that, yeah. The other nice property is the right-hand side of the primal does not appear in the feasible region of the dual. It only appears in the dual. And this is what we use to teach sensitivity analysis in our classes, because basically what do we say? You solve this problem, and then your manager comes to you and says, oh, B changed. And so what can you do? Well, you say that I will store a solution, my dual optimal solution, and now with the updated right-hand side changes the objective of the dual. So this product gives me a lower bound to the updated problem, right? And if B doesn't change too much, this should work well. It does work well in practice. Is this fine? Okay, so we want to do something like this here because that's what you're thinking. You're thinking of IPs with changing right-hand sides, right? All right, so if we have to implement something like this, the most natural way to think about it for IPs is I'm going to take my IP. Well, I don't have a dual, right? But I can use this technology if I work on convex problems. So I'm going to take my IP, I'm going to relax it to a convex program, right? And then I'm going to take the dual. I mean, for example, if the x's were binary, or I just relax the binary condition, I would have like the LP relaxation, which will be bound, and the dual will give me bound. Okay, but of course, you see that if in order to get a strong dual, there is the problem because I'm going to have leakages here and here, right? So this will not be tight, right? And then, in general, this is also not tight. Linear programming, this is always tight. But if it's a general cone, we all know that we need something more like a Slater condition or something like that. Okay? So how do we fix these issues? And so we will sort of build on the shoulders of giants, and there's a beautiful theorem by Sam Buehrer about 15 years back, where he proved that any mixed binary QP, so binary with mixed binary, so you have binary and non-negative variables, and objective is arbitrary quadratic, you can rewrite it exactly as a convex conic program, okay, over the completely positive cone. And if you're sitting there and wondering, okay, that sounds fishy because this was NP hard, this becomes a convex program. Well, it's not fishy because this is a nice cone in the sense that it's full dimensional, closed, pointed, all of those nice properties, but you cannot actually separate on this cone in polytime. All right, so you don't, if you can't separate on this cone, you don't get polynomial time solvability. It's just a reformulation. But it's a reformulation with no gaps. And so now we can exploit this and say, can we take the dual of this conic program, because it is a convex program now, and see if, what is the gap, or can we say something about that? All right. So maybe, since we have some time, oh, wait, we don't. How much time do we have?
40 minutes.
40 more minutes. Oh, wait. And the other 7 hours. Okay. Right, okay. All right, 40 minutes, I think we can do this. Okay. So, so let me just because I didn't want to rush through. I just want to give you a sense. The next few slides, I warn you, is overload of notation. I don't want you to remember the notation. I just want to get a sense of what's going on. Okay, so that's why I have the next few slides. So this is our mixed binary QP again, and this is how Sam Buehrer constructs this conic program. Basically, what you do is you sort of think of writing the standard SDP relaxation, which is you go to this quadratic space, right? You go to this space of products of variables, and so this is sort of my products of variables. This is just my original linear constraints. This is just each linear constraint multiplied on both sides. Because it's equality, I can do that. And this is the classic thing you do in SDP. You say that xi, if x is binary, then xi squared equals to xi. So the diagonal elements of your matrix is equal to the sort of and so that is that. The catch is, now this, of course, you could just say is PSD. This would be sort of like a PSD matrix relaxation. Instead of that, you say it's completely positive. And what is completely positive? It's basically a cone of matrices which is actually a subset of PSD matrices. It's a positive semi-definite matrix, except when you write its gram decomposition, each term is non-negative. All right, so it's the product of non-negative matrices are called as completely positive matrices. Okay, and even though it kind of looks like PSD matrices, it's not that nice complexity-wise. We can't separate on it, we can't optimize on it, and so forth. But there you have it. This is actually a bona fide convex conic program. And I'm going to, in the next few slides, I'm going to change the notation. The x1 is ugly, so I go to y, but these are the same constraints. Just, and as I said, don't focus on the notation too much. It's not going to be very important going through, but I'm just going to use slightly different notation. And this is what Sam Buehrer proved, that you look at the IP, it's exactly equals to this, completely positive. All right, very good. Any questions? Okay. Yeah, and all of this I wanted to show you because I wanted to show you this, because I find this fascinating, okay? I don't do convex optimization, I struggle with even basic concepts, but one thing the convex optimizers have done that's great is they've taught us how to take duals. Okay, a few years back I could not do. I still cannot do if you give me a general convex program, but if it's a conic program, I can take dual. I love that, okay? So this is Sam Buehrer's reformulation. It's so simple. You just put dual variables for every of the constraints. And then just like LP, you write out the LP constraints. And all you do is you take the cone and you flip it and you write the dual cone. Okay, and what's the dual cone now? It's called completely positive cone, which is the cone of, again, looks like PSD, but now this is a larger cone. This one was a smaller cone. This larger cone is basically matrices. When you compute a quadratic form, it's non-negative, like PSD matrices, but you only need to check for non-negative vectors. Okay, so therefore it's a larger cone. And I just want to point out one thing. The right-hand side of our IP appeared in two constraints, sort of linearly and quadratically. And now you see that they appear only in the objective. So they appear here and here. Right? They don't appear in the feasible region, just like we wanted. Okay? And so I set it up. And the question is, do we have strong duality? Right? As I said, even for PSDs, we don't in general have strong duality. We need Slater condition. And we want to ask, is there a hope of getting out of that? And it turns out we can prove. So what our result is that if you look at this class of problems where either the objective was convex, it's not a convex program because you still have discrete variables, or your objective will be arbitrary quadratic, but your feasible region is compact, which means Well, some binary variables are just bounded, but the continuous variables are also bounded, in which case you're allowed to have just arbitrary non-convex quadratic. Then in fact, you have that, the completely positive program and its dual, the co-positive program, their value is equal, and this is independent of any Slater assumption. So you don't have to worry about Slater. Okay? With Slater, it's obvious. I mean, you would get, if you had Slater, you'll have they are equal, but you don't need that. And in fact, in the case where the objective is not convex and the feasible region is unbounded, we can explicitly give examples where strong duality does not hold. Obviously, in those examples, Slater does not hold. So when we did this, so that was that. When we did this, we realized, actually, sort of a year back, few months back, David, who's now at Purdue, and co-authors actually proved this result for the bounded case, but their proof was not constructive. And essentially, actually, it turns out in the bounded case, you can always show there's a Slater point. Okay, so there's actually a more straightforward proof. But I'll talk a little bit about this non-constructive stuff in the next slide. I do want to mention this paper by Merve, Chung, and co-authors, and we were motivated to look at this dual because of this paper. It's a very nice paper. And they were applying this for some power system application again, but this was for pricing. And they were actually trying to use these co-positive duals to do pricing, just like in LP we do shadow prices. And they empirically observed that this was always true, okay, in their paper. And so that sort of really motivated us. And Jeff, no talk is complete without mentioning Jeff. Jeff and Arvind also were at some point in time looking at some of these things. There was a nice informed talk on that. Okay, so actually our result is a bit stronger. It's not just that we prove the dual. Our result is constructive in the following fashion. If you give me that binary QP, and you give me any lower bound, okay? For example, maybe you don't solve the problem, you're using branch and bound, you go, you get your favorite chai, you have some upma with chutney, you come back, it's still not solved, but time is up, you stop it, and you get a lower bound, right? You can use that lower bound, and you can show that you can construct a valid solution of the dual, the copositive dual, whose objective value is L minus epsilon, where epsilon is something positive. And you can do it in a constructive fashion. Like I actually have a recipe for doing this, literally. I mean, not literally, but sort of literally, okay? Like there's a lot of calculations. I don't know, do you call it a recipe or not? But nonetheless. So that's really got us excited for two reasons. One, this actually reproves Burer's theorem for the case of bounded feasible region or convex objectives. But more importantly, as you might have guessed, now I can do sensitivity analysis almost like linear programming. I'll start solving my problem. I don't even have to solve it to optimality. I run it at some point, I stop because I'm tired, it doesn't solve. I get a lower bound, and using this lower bound, I can construct this dual in the copositive. And remember, once I have this dual solution, it's plug and play, right? Just like in a linear programming. I look at perturbed right hand side, multiply it to my dual solution, and this is great, okay? When I was giving this talk a few months back, the analogy, and some of you are here, so please laugh on the joke again. I said this was sort of like a romantic comedy, right? You start watching, and everyone's happy, but then you look at your watch and you're like, only 45 minutes in, something's going to go wrong, right? It's a bit like that. We were super excited. And then this is what we discovered. So there is a challenge to this idea. There's no wrong proof, mistake in the proof, hopefully. I mean, maybe there is, but this is really the real problem. Okay, so you see, checking a matrix is copositive is NP hard. So this is not easy. So somehow our proof is somehow very cleverly, that's in quotes, basically encoding the fact that this was the correct lower bound to construct a matrix that's copositive. Checking a matrix copositive is NP hard, like really. So what we are doing in some ways, this is how it looks like. If your original problem has m constraints, then you have at least an m-dimensional subspace where the following happens. You have some fixed part of the solution that we construct, which is not copositive, but has the right objective value. It's precisely that L that I gave you minus some epsilon dash, okay? And then what you do is, you look at these directions and you travel in these directions. And because it's a closed form solution, we travel like quite heavily along these directions until we hit the co-positive cone. Okay, but because it's a proof, these lambda values there is actually quite large, and we hit this co-positive cone sort of very much in the interior. And basically what I'm saying is these R's have no objective value, and so this is like recession directions with no objective cost. And so this whole, you can think of this yellow region here as like this face where everything is optimal. Okay, and so we start in our proof with some fixed point which is infeasible, and we travel along these recession directions very conservatively so that we can prove that it's somehow co-positive. Okay, why should this be a problem? So here's unfortunately where these things work. So fixed part plus traveling along these directions. Okay, sorry, my graphic is really not very nice. Okay, there was supposed to be a value function of an IP here, which you can hardly see. I'm sorry about that. But these dual bounds are quadratic in nature. Okay, there was a bi and bi square, right? So as you perturb the right-hand side, the function that you get is quadratic in nature. What happens is that if these lambda values are very large, by the way, these are all optimal solutions. So you see all these curves I've drawn, they're tight here at the value function point. But what happens is as these lambda values increase and I go more and farther inside the co-positive cone, this quadratic thing kind of starts collapsing. And in practice, if you use the formula that we use, it kind of looks like a thin line. It just sort of spikes up and spikes down. Okay, so it's not useful in practice. Because if it's something that goes like that, well, if I perturb right-hand side, the lower bound I get is really not that. Okay? And so there's no free lunch, unfortunately. So what we really have to solve, apologies, I don't know how to get rid of that. Can you read this? Yeah? Okay, you guys have great eyesight. What we have to do really is, let's do the picture. What we really want to do is, we know how to construct this fixed point, which is not co-positive, and then we really want to show is how little do I have to travel so that I become co-positive, right? So I can actually solve a modified co-positive program instead of my original co-positive program that does that. Okay, is this idea clear? Unfortunately, it becomes a co-positive program, so there's no free lunch in some sense. All right. So let me give some very preliminary computational results, and I know there are experts here who are certainly going to frown upon these results, and that's totally all right. These are extremely small, and the reason that they're extremely small is because I don't know how to solve co-positive programs. And I was really hoping that something like the closed form would work, but it does not. Right? I still have to solve this modified co-positive program. But the computational results here are to more show you that if we could solve these co-positive programs better, if we could find these dual solutions well, do we actually get good sensitivity analysis? Okay? So the first class of results is stable set on a bipartite graph, which is actually polynomially solvable. But turns out if you add a cardinality constraint, it becomes NP hard. And this is a very natural problem. I just want to change my cardinality. Is the setting clear? Okay. Again, very small graphs, very small instances. But I think I just want to show the picture. The blue curve is the actual value function. Okay. Delta k is 0, and as I increase k, the blue curve goes that way. Okay. It's a little messed up because the objective was min. So throughout this talk, I'm always using min, and sometimes that means I use a negative objective function value, so it's a bit messed up. These three are some other relaxations, and you do the dual. The first scheme we said where we'll have leakages. So I think one of them is just the LP, one of them is sort of sums of squares order 2 because that's what it looks like, and the other one is just cube SDP. So these are the bounds, and you see the purple curve is what we get from the copositive. And you see it really tracks and gives a very nice lower bound for a large variety of right-hand sides. Okay, so if you can find this expensive dual, it's really easy to just plug and play and get a very nice dual bound. Okay, and we have more experiments. I think I don't want to go through numbers, but one more class of problems that appears a lot in IP is you have continuous variables. Here x's are all continuous. They're satisfying some constraints, but the continuous variables are controlled by binary variables. Right? This appears in a lot of applications, fixed charge network problems we call them. And now sort of the data is this in this continuous part. So I'm going to actually change sort of like LP style, the right-hand side is the continuous part. But of course, there are discrete variables controlling, and there's some fixed cost on those, right? And it turns out again, and this one is not visual because now I'm changing instead of one entry, all the entries of this right-hand side. But basically, we have a measure of gap that I'm not going to go into detail, but our gaps are much lesser than some of the other methods. Okay? So let me just conclude this part of the talk. So for operational IPs, I really think we need to think more and do more. Is this the method, this dual? I don't know, I don't think so. But this was exciting. It's a strong dual. I like collecting strong duals for IPs. It could really improve. I really think this could work if we could solve these modified copositive duals really well. We can't solve, unfortunately. And by the way, there's potential to generalize this result furthermore because Sam Buehrer actually in a follow-up paper showed that any QC-QP can also be rewritten as a convex problem, okay? But now the cone is even more complicated, but never mind, okay? And so can we extend some of these systems, right? I have 45 minutes left.
7 hours, did we say that?
Okay. 20? 20 should be 20, 25. Okay, great. Are there any questions? Yes.
Yeah, so you said like it's hard to optimize over
The copositive. Yeah.
you put some constraints like the rank is about like you.
So, a great question. So, for example, I know that Diego, who's really more an expert on sort of some of these things, I think might be still working on this, but they've tried to do like, Montero-Buehrer style, where you try to solve the copositive program by sort of this alternating method. You assume rank is very low. So there, it's just solving a linear system. It's PSD. Now you have to solve an LP alternatively. But yeah, I don't think, I think the analysis of that is far more complicated. So I don't think there's any concrete in that space yet. But yes, there's some hope that if you assume that it's low rank, but it is supposed to be low rank. And so can you use that somehow? So that's a great question.
Just like extending your duality result, the low rank system, not so clear.
Actually, you're right. Yeah, it's not clear. It's clear for I think the copositive, the original copositive, but for our modified copositive, yeah, I don't know if it's a low rank solution. You're right. So yeah, so that might be other challenge. Yeah, but yeah. So I know Diego, for example, and there are others I think who've been thinking of how to solve like Buehrer-Montero style these copositive programs. So there's certainly some like assuming low rank, some action on that space. Yes, sir.
So MIPs can be practically solved
Right.
much better than SDPs.
Yes.
Right. So with the motivation, so
How do I justify it? The justification is, you see, that if I was, if I was solving, let's say, this problem every day, right, and the MIP takes 10 minutes, the copositive takes 3 years, right? But if you still amortize it, because I have to solve it for my lifetime, it is actually better. But that's the idea. The problem with some of these operational problems is not just that, the nice thing is the data remains the same, only right-hand side objective is changing. But really, for a lot of these operational problems, you do have to solve it much faster than usual because it's an operational problem. You really need a solution. And there are certain applications, like, again, motivated by power systems, where they really care about optimality. Because even like a percentage off is lots of money. And so that's the goal. And again, I truly believe, at least from the experiments we have done, if we could solve and store these copositive duals, then in fact, proving dual bounds would be much faster because just plug and play them from there on. But I agree with you that we can't scale, and so there is a challenge. But great point. Are there any questions? Okay, all right, so let me go through the other part, which is actually, some of you might have seen this, but next part is sort of new. I'm presenting it almost for the first time. And so now I go back to this augmented Lagrangian story that we started, but I want to give it a fresh look, okay? And now the purpose is different. The purpose of the previous part was sort of doing sensitivity analysis. Now I really want to think about distributed computing. And again, I know there's actually a culture here at IIT, and there's lots of people who've thought about parallel computing for IPs. So I wanted to present this. So here's a slightly different notation for this part of the talk. yeah, somehow I switched from the transposes to inner products, but you know what I mean. I've written linear objectives, but large part of the this results will actually go through with general nonlinear objectives, and I will say when and when it doesn't. But the way to think about it is curly x1 and curly x2 are mixed integer sets, completely disjoint with two different objectives, and x1, y1, x2, y2 are completely disjoint sets of variables. So if you ignore this purple constraint, they are just two different IPs. Their own sets of variables, that's the sets of objectives. What I'm going to do to this very simple model is going to add a coupling constraint where I say some of the binary variables in the first problem have to be exactly equal to some of the binary variables in the second problem. Okay? And maybe just a few introductory things. It's very important for all our results that these coupling constraints are only on binary variables. And this two block case seems very simple. It is very simple. I'll do most of the analysis on this, but maybe if I have time remaining, I'll show that in fact it generalizes to general MIPS in some natural way. Okay? All right, and this is related to n-fold, but it's not the same thing. Okay, let's get through very quickly. All right. So, what do we do to problems like this? Well, we use Lagrangian decomposition. Why? Because if I Lagrangeify this constraint, it goes to the objective. This is just linear. So now, this is my problem. When I put lambda weights on that constraint, I move that to the objective. That's what it is. Now the feasible region is just literally two disjoint sets. But actually the objective is also separable, right? Because this is linear. Right? So lambda x1 goes into one part, lambda x2 goes into the, I've written everything linear. As I said, this could be more general objectives. Okay, as long as they're separate. And you know, you take the dual, Lagrangian dual, which would be you optimize over lambdas, and you take the best value. Right? Okay. So we know many nice properties. We know that this Lagrangian function is concave function, right? Not only it's concave, we actually know how to compute subgradients, which is just solve these two subproblems, take the optimal solution, and you plug it in the right way, you get subgradients. And then, you know, from the convex optimization world, there's some very nice algorithms, subgradient algorithm. In our experiment, bundle methods really worked well. So that's very nice. So it's a very nice combination of convex optimization, sort of at the master level, and you solve these subproblems individually on these two different sets of variables, which is an IP. Okay? So what's the catch? This is very nice. It actually works really well in practice. So, you know, to motivate that, this is a very nice characterization by Geoffrion, which basically says this Lagrangian dual, the value you get is precisely the value when you optimize this. This is now true only for linear objectives. You take this, or concave, I would say, maybe, yeah. Well, let's stick to linear for now in this slide. Each of these sets of variables are convexified separately. And then you add this constraint from outside. Okay? And what does that mean? Just bear with me. This is the real problem you want to solve. Because your objective was linear in this case, you really want to convexify your feasible region, you get the right bound. But convexifying the feasible region means convexifying each of those individual IPs together with the fact that x1 equals to x2. Okay? And what Geoffrion says is, Geoffrion's results is more general, but applied here, says that what you're getting is convexifying on this part is great, but this sort of goes outside the curve. Okay? So if you have not seen this, yeah, this is a classic result, very nice. I would say look at Wolsey's textbook, beautiful, nice, elegant proof. And because of this Lagrangian dual value, you know, is not tight. Okay, and this is not surprising, it's a non-convex program. And so, what we'd like to do, okay, maybe first let's talk about it. If I completely ignored the block structure and gave it to my favorite solver, well, then there's no gap. Okay? Or even like, but what's the problem? The problem is I don't exploit the decomposability, the natural decomposability in the problem. On the other hand, if I use this Lagrangian decomposition, this really works well in practice. I can exploit this decomposability, but there is non-zero gap, as I just showed you. And so, of course, greedy that we are, we would like to get both of these facts. We would like to have a method which is decomposable and has zero duality gap. Okay? And I'm looking at Pierre, and I feel like this is, I'm going to read his brain, and I'm going to say this is the question he's asking. The question he's going to ask right now is, why can't you do DP? Okay, you can actually do dynamic programming. And actually, in more general setting, it'll be very natural. There'll be some tree widths and so forth. And upfront, I will tell you, yes, you can do DP, where you can solve these subproblems and do some sort of a DP table. The challenge with DP is that DP's running average time is equal to its worst time. So you run your DP, again, go for your snacks, which I do a lot every day, obviously. Come back. If your DP table has not run, if you stop it, zero information. Okay? So what we want is a method which, even if we get strong duality if we ran it for long enough, but okay, if you stop it in between, you'll get something. Okay. So let me give you some intuition, and I know this has been really long already, so I'll try and wrap up soon. So I have two sets of variables that are supposed to be equal, both binary. So what I'm going to do is actually try and think what happens if to the primal I add redundant constraints, which are implied just by this part. The redundant constraints, the only thing I'll require is that they are of this form, some function of the first variable plus some function of the second variable, because then when I dualize, the Lagrangian dual is still separable. Okay? So as an example, here's what I can do. They were all binary. This guy was supposed to be equal to this guy was supposed to be equal to this. So we see that this is a valid inequality, which is implied just by the fact that they're equal and they're binary. I can add this and I plug this into my problem. Obviously, nothing changed on the primal. This was just a redundant constraint. Now I look at the dual. So I had my original duals. Now I have this additional dual, a variable corresponding to dualizing that constraint. This is still separable. Let me call the new dual as dual dash. Okay? And I wonder, is the objective function value of dual dash equal to dual? Okay, and this is, I'm just showing you can now solve this again separately, okay, because of the way the constraints are. So here's our first observation, is that if either of these functions is actually affine, then you gain nothing. Then dual is actually equal to dual dash. So in our example, because one part was affine, which was not nonlinear, basically we'll not get any dual improvement. But what does this mean? This means that if you have to get any improvement on dual side by adding redundant constraints, you have to enter nonlinear territory, right? And that's what we'll do. So the first method that we propose looks very much sort of Lasserre sums of square RLT style, where what I'm going to do is I'm going to have monomials on both sides and I'm going to equate them. So for example, if I had x1, x2 on one side and x1, x2 on the other side, earlier I was just saying x1 here is equals to x1 there, x2 equals to x2 there. Additionally, I'm going to say x1 times x2 here is equals to x1 times x2 there. Okay, now this is a nonlinear on both sides. Just a comment, although this looks like RLT, this is different from traditional because I would do something like this which would not be linearizable. Also, when I presented last time, everyone got confused by RLT, so I want to mention this more. We are not going to do any linearization. So this is not really RLT. It just looks RLT-ish in some sense. But everything looks like everything else. So, all right. We propose one more thing that I'm going to skip, but I would say at a very high level, this kind of imitates some sort of no good things going on. You take any vector in your 0, 1 cube, and then whenever you have a 1, for that you put the variable. Whenever you have a 0, you put 1 minus, and then you equate it on both sides. Okay, they're somehow equivalent, but this leads to a different column generation type algorithm. I just mentioned this because I'm going to do some computational results with this. I'm not mentioning theoretical properties of this. Let's just go back to the monomial style, which we call as M Lagrangian. So what we can prove is if you add all the monomials, right? If you had n variables, you look at all possible monomials on each side and you equate them, then in fact, dual is equals to dual dash. Is the result clear? So if I had, let's say, 5 variables, which were equal on both sides, so I would take every degree 2 terms, every degree 3 terms, every degree, and then equate them all the products. Okay, so I know you're thinking, and I agree with you, exponential number of constraints and variables, yes, true. But at least from a complexity point of view, the way to think about this is each block is somehow of constant. It's very small somehow. It's something you can deal with, and you have lots of blocks. I know we have just 2 blocks here, but in a second, you'll see we can do lots of blocks. Okay, so from a complexity point of view, that's one way to think about it. But I will present some results when you don't go all the way up to full monomial. Okay, and maybe in passing, I'll say the other Lagrangian dual also is tied, but let's skip that. I don't think we should do a proof. No, I feel like as you notice, I will not die soon, so I'll stand here for very long. Okay, let me just very quickly try. By the way, if you have more questions about the proofs, I can go through them. I have lots of other slides. I have lots of slides. But I thought this was very cute. Okay, so I let me try and tell you why this monomial works. Literally, you can see it in 2 seconds. Okay, so this maybe bear with me. Okay, so now you'll see the proof works in general. Again, I've written linear objective, but you could just have any general objective. And then you think about each of those individual IPs as functions of what the value of the common variables are. Is this notation clear? I have common variables, right? So I fix the common variable and solve for it. Okay, for the first one or second one, that's F1 and F2. Now the problem might be infeasible, but if that happens, there's a simple fix. I'm not going to go through that. Let's assume that for every fixing of x, I can compute this is finite. Then what I have is essentially a pseudo-Boolean function. I have a function that goes from these fixings to some real valued number. Okay? And if you think about it for a second, if you have not thought about these things before, any pseudo-Boolean function has a representation like this, using just the monomials and weights on that. Okay? If I give you any function that goes from the 0, 1 box, right, to a real number, you can always write it in terms of monomials. It's a very simple exercise. Okay, so let's write the second function in terms of some weights of those monomials. I know my opt is greater than this dual opt. And what is dual opt? It's maximizing over all dual multipliers, minimizing inner function. And this is all the monomials possible that I'm equating times their dual values. What I'm going to do is I'm going to plug in this particular dual multipliers. So of course, I was maximizing over all of this. So this is certainly better than this value, which is when I plugged in these particular values. But now, notice that because there's symmetry, this is precisely the same minimals on the first variable and the second variables, and the same dual multipliers, what I get is these functions 2 evaluated on the first local variables and second local variables, these cancel out. And then what you get is minimizing over x1 and x2, but really what you're doing is optimizing the first function on first variable and the second function also on the first variable. And so that's just jointly optimizing them, and that's all. Okay, so this is really a straightforward argument. Okay, I will really run through these because I don't want to, die. Yeah, okay. Again, this funky notation read min, but it turns out for packing and covering IPs, we can actually analyze what happens as the degree goes up. What we show is that the dual, of course, is not equal to the opt if you go only up to degree k monomials, but you can actually give a bound on how bad the dual is. And this approximation ratio kind of looks like this, which is not great because in some sense what this is saying is that most of the improvement is towards the higher end of the degree. But this is such is life. Yeah. All right. Okay, let me even skip this. Let me, in 30 seconds, give you a sense of why this so simple setting can be generalized to basically any MIP. Well, not every MIP, but mostly. Here's what you do. You take your favorite MIP, and maybe this is how it looks like. Okay, there are 6 variables, and these are the constraints, and these are the non-zero entries. What you do is you draw what is called the incidence matrix. intersection graph of the adjacency. Okay, so in other words, if there is a node in this graph for every variable, and when 1 and 2 have non-zero coefficients in a constraint, 1 and 3, there's an edge between 1 and 3. Okay, and then what you can do is take this intersection graph and construct what is called as a tree decomposition of this. Okay, maybe I'll just, yeah. I come from Atlanta. Atlanta is very famous for, if your family ever visits, the only thing you do is you take them to the aquarium, which is a great aquarium. But whenever I go to the aquarium, which apparently I go often enough, is I look at the fish and I always wonder what they're thinking. And sometimes when I'm teaching or I'm doing a lecture, I feel like the fish. So I know when to stop. Okay, but bottom line, you can do this tree decomposition and you can look at each node of this tree decomposition. For people who know, each node is a bag of variables. And then what you can do is you can write a small sub-problem corresponding to each bag of this node. Okay, and then in the tree decomposition, every edge, you will have some common variables which are, and then, so you can basically write the whole setup again. And it turns out you can prove the same theorem in this case. So you write this decomposition using tree decomposition, you make local copies of your variables for every bag, and then you have common variables across each edge of this tree. And for these common variables, if you go up to all the monomials and you get them, you get this thing. And so basically, if you have a tree decomposition, you can basically solve for every bag as a subproblem. And you can do monomials between them, okay, at a high level. And this, as you see, I really didn't think I was going to get to this slide. And so the font was small, but let's skip it. But all of that analysis for packing and covering goes through, right? Let me finish in 30 seconds. So is there any hope of making this work? Because monomials are crazy. We can't solve. So again, the thinking is, can I solve these small problems? So here's what we did experiments on. We thought of problems with 10 blocks of stable set, okay? Each block has 100 variables, and these are 2 experiments. This is sort of your stochastic programming setting. Each block has 3 sets of variables, 1/3, 1/3, 1/3. And this, in the stochastic setting, the first 1/3 variables in each block are equal across each of these stable sets. Okay? And in this path setting, right, what happens is the last 1/3 of the variables of the first block must equal to the first 1/3 variables of the second block. The last 1/3 of the second block has to be equal and so forth. And so that's the path, right? It turns out we can do these decompositions in all of these cases and everything works out. Like I said, we tried the classical Lagrangian. We cannot go to all monomials, so we just tried the first thing that you would try, the quadratic. And this vertex I didn't talk about, and we tried Gurobi. We solved the Lagrangian problem using bundle method, but pleasantly surprised that even with a very nice, by the way, this is a bit embarrassing, but all of this talk was about doing parallel computing, but we actually use sequential. All right, so the results can be far better if you actually implemented it with parallel computing. But okay, so we gave 1200 seconds. These are, if you look at it from Gurobi's perspective, it's actually fairly large instances. Like for example, if you look at the stochastic program, there's 100 variables in each block, but there are 10 blocks, right? So there's 67 which are not equal. So that's about 670 variables. So it's about 700 variables. Right, so after running it for 1200 seconds, you see Gurobi which does not use any decomposition, shows a gap of 10%. A Lagrangian shows a gap of 6%, but you see that the quadratic gives lower gap. And in fact, I didn't talk about this, which sort of looks like column generation gives even lower gap. The path one is even nice. If you see Gurobi was 10.5, if you just did Lagrangian 3.5, but in fact just doing quadratic was 1.2. Now, one thing I will tell you is I don't know what the actual gap of Lagrangian is. It did not converge. And this is part of the problem with these convex optimization problems is the convergence is really slow towards the end. So I don't know whether this is all Lagrangian can do or we ran it for another 7 hours, we might get better results. All right, so maybe I will stop here. Thank you, and if you have any questions.